Hello everyone, I hope everybody is doing well and healthy. I'm Tiam and it's my honor to be at this conference with great scientists and audiences from all over the world. Good time to all, and I appreciate all previous presented great works and suggestions. About my background in brain stimulation, I like to say that I became familiar with brain stimulation applications after my master when I started to use for the first time tDCs simultaneously with cognitive tasks for patients in brain and cognition clinic in my country, Iran, as some might know it as Persia, and we got lots of good results. That's why I'm working now in the group of Professor Nietzsche at IFADO in Dortmund, Germany as a PhD candidate. And today I will be discussing the latest finding from an EU-funded Luminous project. The focus of this research project is to develop new and novel stimulation techniques for exploration and alteration of human consciousness. And we are proud to be part of this exciting work. As a background, we all know that our brain is actively firing millions of neurons, and when we measure this activity over a period of time, we get patterns of brain oscillations. From EEG and MEG studies, we think that this oscillatory activity and synchronization might be relevant for many important cognitive functions such as motor coordination, information transfer, memory, and plasticity. At the same time, we also have some evidence that abnormal oscillations are associated with neuropathological disorders like Parkinson's disease, epilepsy, and disorder of consciousness. Since imaging studies do not give us direct causal evidence, a recent trend in the field has been to look at using brain stimulation in order to alter oscillatory activity directly. The goal is not only to understand cognition but to treat neurological disorders. For modulating oscillatory activity, there are two main techniques which have been developed. One is rTMS, which uses high intensity electromagnetic pulses to induce neural activation and oscillatory activity, although this is short lasting. On the other hand, we have tACS. With low intensity tACS, the oscillatory activity can be amplified in the brain through entrainment, but this technique is less effective when there is no endogenous oscillation at the target frequency. This is problematic. Why? Because in many neurological and psychiatric disorders, in many of them, oscillatory activity in relevant frequency bands is diminished or completely absent. So tACS might not be very suited. Therefore, we had these questions whether it might be possible to combine and synchronize these two techniques in order to induce and stabilize any desired frequency in the brain. If we could achieve this, then it might be possible to bring these techniques to research and clinical applications. In order to combine these two techniques, we need to first develop a way for both stimulation techniques to synchronize with each other. Otherwise, the effects from one stimulation might interfere with the other. In a first step, we built an electrical circuit where rTMS pulses could be synchronized simultaneously with tACS. As you can see here, we designed a montage where TMS coil was placed directly over the top of each tACS electrode and delivered pulses in phase with tACS. And And in the first set of experiment, we applied a stimulation at 10 Hz over the prefrontal cortex and measured changes in resting EEG, resting state EEG activity before and after stimulation, as you can see here. And we found that phase synchronizing rTMS pulses to the peaks of tACS sinusoids resulted in an enhanced and lasting increase in 10 Hz oscillation, which was more effective than each stimulation protocol on its own. Also, the effects was not observed when rTMS was synchronized to the throat. Given this first promising result, we were now interested to use this combined stimulation protocol for exploring causal relationship between oscillations and cognitions. In this view, we looked first at whether we could also enhance resting state prefrontal theta oscillations with our combined stimulation protocol, and secondly, whether such a prefrontal theta enhancement could also be directly linked with improved working memory. I will go through the results of each experiment one by one. In our first experiment, we look at whether phase synchronizing stimulation could enhance resting state EEG power. In this experiment, we had 25 participants who took part in 6 randomized sessions, and 6 Hz rTMS plus tACS was applied over the bilateral prefrontal cortex, and our stimulation protocol was 20 minutes continuous tACS plus 30 seconds on and off rTMS, and we recorded EEG in eyes open and eyes closed conditions at baseline, and also every 10 minutes after stimulation up to 60 minutes. In order to quantify the effects of combined stimulation, we compared our combined stimulation with other protocols, which each stimulation protocol was on its own. And as well as to a protocol completely sham. We also included 2 additional protocols for exploration. One protocol was theta gamma 80 Hz by 6 Hz cross frequency cup tACS waveform, which has been demonstrated to be involved in working memory processing. A second protocol was to explore whether after effects could be sustained longer by intermittently continuous tACS every 5 minutes. We found that when we compare changes in 6 Hz power to sham stimulation over the 60 minutes time course of the session, all 3 combined protocols showed a significant enhancement in power in both eyes open and eyes closed condition. The grand average change in 6 Hz power for 60 minutes shows that in both eyes open and eyes closed conditions, the 3 combined protocols showed significantly enhanced 6 Hz power relative to each protocol on its own and to sham. When we look at changes in 6 Hz activity over the whole brain, we found a pattern of enhanced power in both frontal and parietal region. In order to assess whether these changes were functionally coupled, we measured changes in the functional connectivity between these two regions. And functional coupling was enhanced with the three combined protocols relative to sham stimulation in both eyes open and eyes closed condition. So the conclusion from our first experiment was that we were able to enhance 6 Hz activity over the prefrontal cortex by phase-synchronized rTMS and tACS with effects lasting up to 60 minutes after stimulation. Moreover, we also found the network effects in the frontoparietal regions, which suggests that these stimulation techniques might be useful for altering network activity. With these positive findings, we then asked the question of whether these techniques might also be effective for functional outcomes in cognition. Specifically, we thought about working memory, since it's shown to be directly related to theta activity. So in the second follow-up study, we conducted the same stimulation, but this time we asked the participant to complete the 3-back letter task before and after the stimulation. When we computed the results, we found that both the combined rTMS plus tACS protocol, as well as the rTMS plus tACS theta gamma protocol, significantly improved overall performance accuracy on a 3-back. On a 3-back task as measured by D prime statistics when compared to sham stimulation. We also found a non-significant trend where the combined rTMS plus tACS protocols also decreased reaction time, meaning that subjects did not only perform more accurately but also slightly faster. So to conclude, we are able to demonstrate that these combined techniques also result in functional changes to cognitive process like working memory. Specifically, we found that rTMS plus tACS over the bilateral prefrontal cortex with both 6 Hz tACS and also cross-frequency 6 and 80 Hz tACS protocol could enhance working memory performance, although there were no significant difference between these two protocols. These findings are still in their early stage, and we expected to carry out more work in this line, like studying the mechanism behind the after effect and whether they depends on synaptic mechanism, and also we are interested to experiment with the stimulation parameters in order to further optimize the protocols. Taken together, we believe that this phase-synchronized oscillatory stimulation could be a viable approach in cognitive neuroscience for directly exploring causality between cognition and oscillatory activity, and also as a therapeutic approach for clinical cases of abnormal oscillation, like in epilepsy, major depression, or disorder of consciousness. With this slide, I want to thank all my colleagues, friends, and family who helped me in and support me in this project. And this is my email, and I am open to any idea or collaboration. And if there is any question or comment, I will be happy to hear that. Thanks for your attention.